So another shifting gears mechanism here where we're going to see some chemistry that we haven't seen yet, but what I want you to realize is that we've seen the themes before. We've seen carbonyl containing compound acting as an electrophile, and now we're just seeing a new kind of nucleophile. We're seeing an amine act as a nucleophile. So I'm just going to go through the mechanism first, and then we'll talk about some aspects of it. So again, have an amine here. And remember, the thing with amines as compared to, say, alcohols is these are fairly good bases, which also makes them good nucleophiles. Because they're good nucleophiles, when we have something like a carbonyl, which normally isn't a great electrophile, we don't want to see any protonation here. First of all, because we don't necessarily need it, and second of all, any protonation is going to protonate this amine, and it's going to eliminate its ability to be a nucleophile because it'll now be missing that lone pair of electrons. So theme is similar to what we've seen with many of our mechanisms here. Nucleophilic attack on a carbonyl of a carbonyl-containing compound to generate a tetrahedral intermediate. And what we're going to see here is, again, we're going to have a unique situation, and we had a mechanism before where we highlighted where we wouldn't necessarily see positive and negative charges on intermediates, but this is a case where it is warranted because, again, we wouldn't want to put ourselves into an acidic environment where we would protonate that carbonyl, because that would also protonate our nucleophile, which would be problematic. It wouldn't be unreasonable to kind of show the simultaneous protonation of this guy with nucleophilic attack. So as we'll see here, this first sort of protonation of this intermediate here is sort of possible to happen at the same time as our formation of our tetrahedral intermediate. But in this case, not too worried about having a situation here where we're going to have these protonation and deprotonation events happen at the same time here. So again, deprotonation of what was our incoming nucleophile to sort of eliminate that, and then protonation of our tetrahedral intermediate generates what we call a carbonylamine intermediate. So let's draw that out here. So again, this is a carbonylamine intermediate. So as we've seen before, when we have an OH group here attached to a carbon atom, again, that was our carbonyl, protonation of this guy can make it a good leaving group, and if there's an internal nucleophile that can push it out, we're going to see that chemistry happen. So first, let's go ahead and show the protonation of this to make it into a good leaving group. My stuff is getting a little bit scrunched here over on this side. So now again, if we've got this internal nucleophile, can push out our good leaving group here. We're going to lose water. And we're going to generate an intermediate here that we're going to call a protonated Schiff base. Whoops. So again, an amine here that is protonated as an imine, having that carbon-nitrogen double bond. We call this a protonated Schiff base. So we can show deprotonation of this Schiff base to get to a neutral intermediate. So again, deprotonation is going to get to the imine Schiff base product that we're looking for. So this again is a Schiff base. So again, just highlighting some chemistry that is similar, right? Carbonyls are good electrophiles. We've got a good nucleophile and a base, generating a tetrahedral intermediate that through proton rearrangement generates this neutral carbanolamine intermediate. Decent leaving group here in a hydroxyl group once it's protonated to become water. Heteroatom with an adjacent heteroatom with a lone pair of electrons can easily facilitate the departure of this leaving group, generating this intermediate here, a protonated Schiff base, and we resolve this positive charge by deprotonation of this hydrogen atom, generating our Schiff base. So one of the things that we're going to talk about, but I want you to be able to see the parallels with, is how this would have been similar if we had had an alcohol here. And in this case, we would have had a protonated ether. We would have been able to do some proton rearranging to kind of generate this ether linkage here, which would have been, in this case, with a ketone, would have been a hemiketal. And again, we had the same sort of departure of our leaving group. So, but then again, generating this positively charged intermediate, this guy would have been an oxygen here. And so in this situation, we would have had a very electrophilic intermediate, and that's where we saw the addition of a second equivalent of alcohol here. So in this case, that was something that allowed us to move forward with the products we were seeing with those mechanisms. So this is, again, a little bit different. How we resolve this positively charged intermediate is we're able to deprotonate. So again, a few comments here. Again, the chemistry should look similar for what we saw when we generated our hemiacetals and hemiketals with the addition of alcohols to ketones in reaction mechanisms 4 and 6. Again, first doing nucleophilic acyl addition chemistry, and then because that attacking nucleophile, the heteroatom, in it being an oxygen atom in these reaction mechanisms, nitrogen atom here, we're going to facilitate the elimination of water. And again, already talked about this, but see these parallels. What happened after we had elimination of water with our acetal and ketal formation, generating that positively charged intermediate, was we were able to resolve that by having nucleophilic attack by a second equivalent of alcohol. Again, this positively charged intermediate that we get using a primary amine generates a positively charged intermediate that we can resolve by simply deprotonating. And so, again, this positively charged intermediate using a primary amine, we're going to see a lot of this similar chemistry with enzyme catalysis, where we're going to have that role of the primary amine played by lysine. Again, resolving that positively charged intermediate happens by just simply deprotonating that protonated imine. We should say that this is a protonated imine. And again, that's a protonated Schiff base, and we generate our Schiff base. So again, just highlighting here, we resolve this positively charged intermediate here by just simply deprotonating, and we get to our Schiff base here. So again, this is an imine. This is a protonated imine. So again, biochemical application, where will we see this in the future? Again, not as much as we're going to see carbonyl-containing chemistry with alcohols, but again, this kind of chemistry we've seen a couple of times already. Sometimes we've seen a useful end product using nitrogenous bases and generating an N-glycosidic bond. That's how we attach the nitrogenous bases to the ribose sugars that we see in nucleic acids. Again, that chemistry stopped at the carbanolamine intermediate because we didn't have that additional OH group to eliminate as water and generate the imine. Where we're going to tend to see the chemistry that we have right here is where we're going to have our imine serving as an intermediate to facilitate some other kinds of chemistry. So Schiff base formation is frequently seen in enzyme chemistry to generate what we call an electron sink. So if we think about this here, this is something that's positively charged, can help withdraw electron density, both inductively because there's a positive charge there, but via resonance because we can move pi electrons around. So these electron sinks help facilitate and stabilize any negative charges that might be developing during a chemical reaction. And so we can see this chemistry when we study the decarboxylation chemistry that generates enolates. We'll see that when we talk about decarboxylation chemistry in a couple of chapters. So again, reaction mechanism 16, kind of shifting in a new direction, but hopefully you'll see these themes from other things that we've discussed before.